FYI, I told him to say that I play guitar, not that I wanted to be an astronaut, but he made his choices. Hi, everybody. If anybody that's still standing up could please sit down quickly, because I do not recommend missing even a small part, because everything kind of builds one on top of the other. Let's begin. I'm happy you had coffee. You are going to dearly need coffee for this next session. We are going to be discussing React Concurrency. React Concurrency is the concurrent model that was introduced to us in React 18. But throughout the session, we are going to see that the fundamentals for the development of concurrent React have been laid down all the way back to React 16. My name is Ariel. I'm a full-stack developer at Illumex. I like understanding how do things work. I also really like my dog. This is my dog, Ginger. She is a backend developer. And I've been researching concurrent React for, I'd say, a few months now, and mainly searching for a simpler way to explain this complex subject. And I think I got it. You guys are going to tell me in 30 minutes. Any complicated subject that we want to understand, I feel like answering the what, the why, and the how is probably a good way at it, and that is also what we are going to be doing today. So we are going to be answering the what, why, and how of React Concurrency. The what would be, what is concurrency? The why would be, why do we need it? So understanding what problems concurrency solve, and understanding why does concurrency solve our problem in React. And last but not least, we would understand how is it implemented. Now, I know what this looks like. This looks like a theoretical talk. It is a theoretical talk. But we are going to see why sometimes understanding theory is the best practical guideline, because when you understand how things work, you don't need to invest time and energy in memorizing a lot of arbitrary rules, because understanding theory just leads you to the situation where the rules make sense. You don't need to remember them, you just know them. No further ado, let's answer our first question. What is concurrency? Now, this is a trick one. Concurrency is very oftenly mistaken to be parallelism. But these are two very, very different things. Parallelism is when you are doing stuff at the same time. SpongeBob is cleaning his house in parallel. Is SpongeBob advancing faster because he's doing these things at once? I'd even dare say that SpongeBob is getting his house messier because he's doing these things at the same time, like dusting your carpet, wiping your window, and vacuuming your carpet. Come on, SpongeBob. Now, explaining parallelism is quite easy. Explaining concurrency, that's slightly more complicated, and it really took me a while until I found an example that I can stand behind on how to explain concurrency. And our example is a small restaurant in California in 1942. This is not a commercial. I'm vegan. Please do not go and have burgers later. But they are just a very good example of concurrency. 1942. The McDonald's brothers, Richard and Morris, redesigned McDonald's because they want to reduce expenses and they want to deliver faster. Now, they are limited in technology, limited in money, but they are very, very creative. And what the McDonald's brothers did was to take their full team for a whole day on a tennis court. And on this tennis court, they tried designing different ways to arrange the kitchen and to distribute the work between the different workers. And what they were looking for was the most perfect flow that would allow their workers to work in harmony, to continuously deliver. It took them around 6 hours on that court, but they found it. They found the speedy system. The speedy system is basically an architecture. It's a way to design your kitchen, and this is basically the invention of fast food, okay? Fast food is, well, concurrency. And already on the first year, the speedy system increased McDonald's incomes by $200K, which was a lot of money in 1942. And they also improved performance from 30 minutes to one burger to 30 seconds. Now, the McDonald's brothers, they would call this speedy system. I would call this concurrency. And because this is what concurrency is really about, okay? Parallelism is just when you are doing stuff at the same time. But concurrency is an idea. It's an architecture. It's about finding the most perfect flow using your current resources so that you can continuously deliver. So, like, things could be happening at the same time, but that's not the point. It's about continuously delivering with your resources. And so, no, concurrency is not parallelism, but concurrency could be used to fake parallelism. So let's see how is this done. We're going to discuss how do operating systems manage when they have more processes running than physical cores on the computer. So let's say that in our example, we have 3 processes running and a computer that only has 1 physical core. What does that mean? This means that for any given moment in time, we could only be working on 1 process. So let's imagine that in our imaginary scenario, at 0 seconds, the VS Code process had to run for 6 seconds. And then at 2 seconds, the terminal process had to run for 2 seconds. And then at 5 seconds, the Chrome process had to run for 3 seconds. If we would have treated this in what's called the first-in, first-served approach, it would pretty much look like this. So it would be this waterfall. And, well, this is not so good. Why is this not so good? Well, primarily, we are in a high risk of 1 process that can monopolize all of our CPU. Imagine that we have an infinite loop in our VS Code. And beyond that, the experience is just not good. Let's explain why. Well, almost any process besides the first one would experience delays in its kickoff. And when a process delays in its kickoff, it creates an experience that the operating system is not responsive. And responsiveness is the first thing in user experience. And we are going to be discussing responsiveness a lot today. Now, so operating systems do not use the first-in, first-served approach, obviously. Operating systems use a concurrent algorithm that is called round-robin scheduling. So round-robin scheduling, it's made out of 2 parts. The first part is scheduling, or time slicing. Basically, what does time slicing mean? The idea is that we would be limited to some certain time quantum, okay? So this means that if our quantum is a quantum of 1 second, any process that we run, we would always run it for 1 quantum at a time. This means every time we run a process, we run it for 1 second. Of course, in real life, we're speaking about times that are a lot smaller, but this is to simplify. So that's time slicing. And the second part of this is scheduling. So the idea of a scheduler is a process that its entire reason to exist is to receive tasks as input and return tasks with their future execution time. Okay? This means this is an asynchronous model. The tasks are not executed synchronously, but rather they are passed on for the scheduler to decide when would they run. The second part of this algorithm is what's called round-robin. Round-robin in English is taking turns. Round-robin from the world of sports, for example, when we call games round-robin. Games that are round-robin are games where the goal is to allow the participation of as many participants in the game. So if we take this back to operating systems, the idea is that as many processes would take part in the game. So every time we run a process for 1 second, and then if we face a scenario where we have 2 different processes, we would always prefer to alternate. And then we alternate back, alternate, and so on. And what's interesting is that the total time is still the same, okay? It's still the same total time like it took us before. But what's interesting is that we changed the experience because all the processes do not experience delays in their kickoffs anymore, and the system seems responsive. And if you think about it, that in real life, because the time quantums are so small, it really does feel like these things are happening at the same time. So I think we answered the first question. We understand what is concurrency. We understand that concurrency is a design that allows us to maximize our resources, that concurrency could fake parallelism if we break our work into very small loads and organize them. And I think we can move on to answering the next question, which is, why do we need it? And I imagine many people here in the room are having the same thoughts. What does any of this have to do with me? Operating systems and McDonald's, and I'm sorry to be the one to break this to you, but this has everything to do with you. Because in fact, in front end, we are dealing with a scenario that is quite similar to the one we've seen at the operating systems. And the reason for that is the limitations of running code on a browser. So when we run code on a browser, we are facing quite a few limitations: JS, FPS, and UPR. So JS, JavaScript. JavaScript, especially run on the client, is a single-threaded language. Some people would say that also on the server, but that's not the point of this talk. So we can only do one thing, okay? It's very similar to the single core example we've seen at the operating systems. Well, not similar. It's the same thing. We can only have one thread. Now, FPS. FPS, it stands for frames per second. This is basically the way to measure how is motion displayed to the human eye. So any motion that you see, whether it's a video game or animation on the browser or a movie, is nothing but a set of images that change so fast that your brain just completes the missing information. And, well, the browser works in the same way. This means that the browser is a flipbook. And the browser flips frames every 16 milliseconds. This might make you think, what if a rendering takes longer than 16 milliseconds? Well, what would happen if a rendering takes longer than 16 milliseconds is what's called frame dropping. Now, it's easy to understand what's frame dropping when we imagine a flipbook and we're dropping some frames. Like, the motion seems not smooth. So this is our second limitation. And the last reason why our life sucks and we need concurrency is the last measurement, UPR. UPR stands for users' patience rate. I invented that. So users are kind of like toddlers, okay? Sometimes they are very, very impatient, and they need everything to happen now. And sometimes users can be cute little good kids. As long as you give them the spinning loader fast enough, they know they need to wait patiently for their content to appear. Now, if we try to differentiate when are users patient and when are users impatient, it all kind of depends on how intensive is their interaction with the component. So if a user is typing or dragging or watching some animation, the user would be impatient. And I resonate. Like, I'm a user sometimes. It is very annoying to type something in an input box and not to see it straight away. Now, in any other scenario that's less intensive, as long as you give them the spinning loader fast enough, they can be cute little patient kids and wait for half a second or something. Summary it all up. We need concurrency because we only have one thread. We are limited to 16 millisecond time frames for a render, and we are dealing with a partly impatient toddler. So you might be asking yourself, how is React handling all of this? And the answer is that before React 18, well, it wasn't. And React 18, basically all the last versions have been around changing this. So let's see what's the flow before React 18. Okay? So let's try to imagine it's like this process bars that we've seen before. We have the urgent process and the less urgent process. And let's say that at 0 seconds, the user types the letter R. He expects to see R immediately in the input box. And then he expects to see the set of results for the letter R. And then the user would type the letter E, and he expects to see RE in the input box, and he expects to see the set of results for RE. I lied. This is not how users work. Users are toddlers, right? So many times, the user would not wait for you to finish rendering your result set, and he would already type the letter before you even finished rendering. And then you also expect to see the input box re-render. Now, when this time difference is big, it creates frame dropping. Frame dropping creates sad users. Sad users create either sad or unemployed developers. So we don't want this, don't we? I want a job. So I think we understand why do we need concurrency, because of the limitations that we are facing. We can start maybe discussing how is it implemented. Well, no, I lied. We can't really discuss it yet. Before we discuss implementation, let's make sure we all see React the same way. I'll explain. Well, React, funnily enough, it's not reactive. I'll explain. We have a to-do state. It's initialized to be 0. We have a use effect. We call setToDo to 3, and then we console log to-do. Everybody together, what would the console log be? 0. You still have jobs. So it's still 0, right? React did not react to this change. And why is that? And the reason for that is a design decision that has been there since day one. When you call setToDo to 3, you are not updating anything. You are just scheduling an update. And I feel like a lot of things get much better the moment we stop expecting React to be reactive and we start seeing React for what it really is. React is a scheduler. React is an asynchronous model. React is the one that has the control over when state updates would be executed. Okay, so you are not in control, React is. And this used to be very, very frustrating that we can't really influence how and when would our state be updated. But from React 18 and onwards, we can be. And this is basically really the heart and soul of React concurrency. It's about giving us the ability to communicate with React over rendering. So being able to tell React that some tasks are less urgent than others, that some tasks could be aborted if unnecessary anymore, or that being able to split tasks into smaller tasks so we can easily stay within our time frames. Now we can start discussing implementation. So we're going to start at the top, literally. root.renderApp. When we call root.renderApp, what happens? This is a recursive function that creates a tree of React elements. This tree is later on used to update the DOM. This process is called reconciliation. And it's made out of 2 phases. So the first phase is the render phase, in which we calculate the tree of React elements, the changes of states and props. And the second phase is the commit phase. So we commit the changes that were just rendered on the tree. The way this used to happen before React 16 was with a mechanism called the stack reconciler. So how did the stack reconciler work? Every time there was a state update, it would trigger a full re-render of the tree, a full traversal of the tree, and all of the changes would be stacked up to this stack, and this stack would be executed synchronously. This is what caused the problems of a user typing while rendering, and we have nothing to do about it. And really, all the versions since have been around fixing this and allowing us to have control over rendering. So the first phase in fixing this was React 16 that introduced us with the fiber reconciler. The fiber reconciler, the idea behind it is that we would not stack all of the changes into one stack to be executed synchronously, but rather we could break this stack into a few smaller stacks. So you could look at it as fibers, you can look at it as virtual stacks, you can look at it as a unit of work in React. The idea was to take advantage of React's abilities as a scheduler, and if React is a scheduler, well, you guys should already know what the time quantum is, don't you? Well, I kind of lied because the browser has some cleaning up work to do, so it's actually a quantum of 10 seconds. But the idea was to allow us to overcome the time frame problem and to be able to split rendering into smaller tasks. And not only that, but also to be able to say, this work is less urgent. You don't need to do it now. You can go ahead and do it later. This is what's called a non-blocking update. We are going to see how do these things happen. Okay? And these are our tools to do everything that I just showed you. So they kind of group along like this. Use transition and use deferred value are around are causing background renders. We would get into everything, don't worry. And suspense is about splitting tasks. Let's see how the suspense look. The syntax for suspense is a component that we import from React. Suspense accepts a fallback component, and it accepts children. And what's interesting is how would suspense look like in our render tree. So suspense would pretty much look like this. Okay? It basically pushes the loader with its parents. Its children are rendered below, but what is really interesting is that suspense is not a component. Suspense is a hole. Suspense is plugging a hole in our tree. It basically means that suspense is breaking a stack into another stack, breaking a stack into another fiber. This is what suspense is, and this allows us to improve our performance by avoiding frame dropping and staying within our time quantum. Now, suspense is easier to explain, I think. Use transition and use deferred value are slightly more complicated. So use transition and use deferred value are ways to cause background rendering. It would be very obvious with the drawing, don't worry. We'll just go over the syntax quickly. So use transition is a hook that returns a tuple. In the first position, we have an is pending Boolean variable, and we have a callback start transition in the second position. Start transition is a callback that accepts a callback. Use deferred value is a hook that accepts an argument and returns an argument of that same type. So what's the idea? The idea is to trigger a non-blocking update. And what's the difference between them? Well, it kind of depends. In use transition, we would want to set the color in the background. Use deferred value, we would want any updates that are dependent on color, we would want these updates to happen in the background. No, I'm saying in the background, but I didn't explain what that means. When there are transitions running or deferred values running, what happens behind the scenes is that what is called our tree, we would now be calling it the current tree. The current tree is matching what we see in the DOM. This is the tree from the rendering phase. Now, when the transition is running, what really happens behind the scene is that this tree is copied into another tree that's called the work in progress tree. And the updates, the background rendering, would happen on a tree that we are not visually seeing. And only when that update is complete, we get to reuse what we already did, and then the current tree would just point at the work in progress tree. So I talked before about aborting work. What does that mean? This means that if we are having a background render and the current tree re-renders, what would happen is that the work in progress tree would disappear and start over again. So imagine we did not see the updates, so we did not see that the updates are also being aborted. This is visually seeing what a non-blocking update would be like. That's what use transition and use deferred value are about. Now, I don't know, I think we understand how is it implemented. I think we have time for a demo. Okay. I didn't think I'd have time for it, so. Cool. So this is a demo that Ben Holmes and Dan Abramov did. I just want to show what is a good usage of use transition, because I feel like you really understand it when you see it. So this is a toy router. This is kind of like a baby app router. Next.js is not involved. And these are server-side rendered components. And the thing is that when we are going server-side, our way to really ask for more components is throughout changing our URL. Every time we change our URL, we request new server components. Now, what's the problem when we do that? The problem is that the URL is the top of our state. So when the URL changes, everything re-renders. This means that if I have an input box, you actually want to see this, not in full screen because you want to see the URL. So, okay, you guys are gonna, it's gonna be a smaller screen. The idea is that every time I type a letter here, it would update my query params. And you saw what happened to my input box? It disappeared, right? The reason is that the whole page is being re-rendered. Now, we don't want that, do we? So, if we would just, we have a set URL, okay? This is where we navigate. And if we would type this update, updating the URL, we would wrap it up in a transition. What this would look like is that the updates would start happening in the background. And suddenly, our URL doesn't disappear. I don't want you to clap me because it's not my demo. And another interesting thing that we have time to see is that this whole component is wrapped up in a suspense. Okay, you see that we have a suspense, and we have this fallback waiting for suspense render. And we are rendering the whole application, right? So we would expect to see waiting for a suspended render every time we render this, don't we? Like we see in the back when it starts. We see waiting for suspended render, but then we don't see it anymore. And the reason is that this suspense is inside a non-blocking update. So what does this mean? This means our suspense pushes the loader to its parent, right? So its loader is also in the background render. And I didn't think we'd have time for the demo. That's very cool. So, guys, I think we understand how was concurrency implemented. Thank you very much. If you want to add me on LinkedIn, thank you.